Mr. Tarou, in this lesson we are going to look at four examples of finding derivatives of exponential functions. I didn't say natural exponential functions, I said just functions, so base A. And if you already know how to find the derivative of a natural exponential function, whether you realize it or not, you already actually know how to do these problems, and I'll show you that as we go through our examples. If A is a positive real number and not equal to 0, and if x is any real number, then the exponential function to the base of A is denoted by a to the x power. The base is a constant and the variable is in the exponent. And it's defined by a to the x is equal to e to the natural log of a x times x. Now I'm going to get back to this as we get to the right hand side of this board. And this is really the line here that says or shows you that if you can find the derivative of a natural exponential function, then you can find the derivative of any exponential function. And I'm going to really hit on that relationship very, very hard as we go through our examples because, well, basically what I'll show you is we have a rule here for finding derivatives where the base is anything other than e, but, you know, it's just another rule to memorize. You can, and the problems go quicker, but you can use the skills that you already know to do these problems as well and save yourself a little bit of memorization. Well, why do we have this condition here of a cannot equal 1, the base cannot equal 1? Well, if we have a equals 1, then y is equal to 1 to the x power, and 1 to any power is equal to 1. So you just have a constant function of y equals 1. And, you know, then it's just a horizontal line. And the derivative is going to be 0. The derivatives for bases other than e, let a again be positive and a real number not equal to 1. And let u be differentiable function of x. For the vast majority of the problems we're going to do u substitution at this point. So the derivative with respect to x of a to the x is equal to the natural log of a times a to the x, or when that exponent isn't just a simple x, then, and you do a u substitution, the derivative with respect to x of a to the u, natural log of a, times a to the u, times the derivative of u with respect to x. Okay, could you hear that noise? Something got dropped outside. Okay, at any rate, let's talk about this change of base here. If I write y is equal to, so kind of like a separate little section here, y is equal to a to the x. Well, I can take that function and apply the natural log to both sides. I'm basically going to show you the steps that it takes to change this base a to base e. So if we take the natural log of both sides, and we then, you know, basically try and, you know, I want to get this left-hand side of the function back to just a simple y. Well, the inverse of natural log is, you know, a natural exponential function. So I can apply or make both sides of this equation an exponent of e to, I want to cancel out that natural log that I've applied to the left-hand side. Now, actually, you could technically argue that it's going to cancel the natural log on both sides, but for the purposes of how we're going to work these examples and matching to this right-hand side, I don't want to get rid of the base of e on the right. I'm trying to make it into a base e so I can apply the derivative rules that we already know. So we're going to let this e and this natural log cancel out on the left, and we have y is equal to, and we can write, you know, e to the natural log of a x, that would be a to the x power. And then applying the power rule, of course, that we know that we can apply to natural logs, we can rewrite this as e to the natural log of a times x. Now, normally, of course, we're used to seeing that power drop out front, and of course, you can write x times the natural log of a. It's just that the natural log of a is a constant, and we normally, of course, put our constant or coefficients in front of the variable. So that's how you go in small steps from base a to base e on our exponential functions. Woo! First example, pretty straightforward. F of x is equal to 2 to the negative 5x power. Okay, well, if you do have this rule that I just gave you memorized already, you can just do a u substitution, because our exponent isn't just a basic x. So we can let u equal negative 5x, and then du, the derivative of u with respect to x, is equal to just negative 5. And again, if this is, you know, right at your fingertips, you can just pull it out immediately and write it, then you can just write your answer. And not do the second way I'm going to do this example, which is convert it into base e. So we have the derivative with respect to x of a to the u is the natural log of a, which is the base. So we could write f prime of x is equal to the natural log of the base, which is 2, times a to the u. So that's going to be times 2 to the negative 5x times du dx, which is negative 5. And our final answer would be negative 5 times the natural log of 2 times, and maybe you want to wrap that in parentheses to highlight you're only taking the natural log of the 2, or you can wrap the whole thing in parentheses, times 2 to the negative 5x power. Okay, great. Unless of course you forget this rule, plus, and just to tie this together with what we've already learned with our derivative of natural exponential functions, we can take this f of x, or y, is equal to 2 times, or 2 to the negative 5x power. Take the natural log of both sides. Make both sides an exponent of e to I want to just show the cancellation of that natural log on the left. Don't cancel it back on the right. We'll be back where we started from. Okay, and you can drop this exponent down, but I want to leave it the way it is because I do want to eventually cancel this. But what I want to do now is, you see the pattern? We have y is equal to e to an exponent that has a variable in it. So basically we're going to do the derivative of a u substitution and find the derivative of e to the u, which hopefully we already know. It's e to the u times the derivative of u with respect to x. So in this format I can use what I already know, just changing the base from base a to base e on the exponential function. So u is equal to the natural log of 2 to the negative 5x. Now I am going to drop this power down and write it as u is equal to, again, we generally want to put our constant in front of the variable, but just to show that use of the power rule is we're comfortable with it, maybe in a pre-calculus class or earlier this year, we're going to have negative 5x times the natural log of 2. Okay, now I'm going to go ahead and turn it around just to use this extra step, and we have negative 5 natural log of 2 times x. Wrap that up there. Okay, so we basically, it's just like me asking you what's the derivative of 2x? Well, it's just equal to 2. So this whole negative 5 natural log of 2 is a coefficient of the x, so the derivative of negative 5 natural log of 2 of x is just going to be the derivative of u with respect to x is going to be negative 5 times the natural log of 2. Okay, so we have u prime is equal to, well, this is e to the u, and the derivative of e to the u is e to the u times the derivative of u with respect to x. Well, the derivative of u with respect to x is negative 5 natural log of 2. And now I can come back and I can go ahead and let this base e and this log base e with no with a coefficient of just 1, so they're stacked, these can cancel. So these are inverse math functions. So the e and the natural log, or the log base e, we can go ahead and let that cancel out, and we have y prime is equal to 2 to the negative 5x times negative 5 natural log of 2, which is perfectly fine way to leave your answer, but to have just that exact match over here, we have, of course, we can move this coefficient out front and get negative 5 times the natural log of 2 times 2 to the negative 5x power, which is what we have over here. Okay. I'm kind of pausing and thinking for a little bit, or just pausing for a second, because you need to keep simplifying just until the point where your teacher requires. A lot of standardized tests, they'll be happy with you maybe stopping maybe right here or right here, where they're testing you on your knowledge of the calculus, not your knowledge of simplifying or working out a few algebraic steps. So, if you have this as correct, some standardized tests and graders would count this as correct. You go through the simplification process and make a small mistake getting to what you feel is the simplified version of the answer. If you make a mistake in that algebra, you could lose a point even though your calculus was correct. So really, either this or this is, could be an acceptable answer for your teacher on, some standardized test that you're taking. But just to continue to teach a little bit here, we can get rid of, or we can rewrite this, this base a little bit. We can rewrite this as -5. I'm going to wrap the natural log of 2 this time, and write this as 2 to the -5th power raised to the x power. Kind of normally when we see these stacked exponents, we're putting them together. Power to power is multiplication. Here I'm kind of pulling it apart, and I can rewrite this 2 to the -5th power. I can write that as 1 over 2 to the 5th, which is going to be, and apply the power. So we could say our final answer is f prime of x is equal to -5 times the natural log of 2, 1 over 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 30, excuse me, I just lost count, 2, 4, 8, 16, 32 to the x power. Now, I'm just showing you this just for, I don't know, for teaching purposes. Maybe you're going in the back of the book and you see the answer in this form, but maybe you were here, or here, excuse me, and you're thinking that you did all this work and you didn't have the right answer. Well, you may have not simplified to the point that your text is using to give you the answers in the back of the book. And again, simplify just to the point where your teacher is happy, or what you could expect to be required to do on some test that you're ultimately going to take, and don't oversimplify, because if a mistake is in there, then you're going to lose points, even though your calculus was correct. Next example. For our next example, and the third example, we are going to need to use the product rule to finish these problems. So let's remind us of what the product rule states. I'm also going to kind of correct a small error in my notation from a video I did a little over a year ago. Not that everyone's going to watch my videos in sequence, but when I did this, I had the second term here, I had these factors flipped, but multiplication is commutative, so with those problems I didn't have any problems with the final answers being incorrect, but it's bothered some viewers that it didn't exactly match what their book said. So here is my product rule as the text that I teach out of states. The product rule of two differentiable functions, f and g, is itself differentiable. So we have the derivative with respect to x of f of g times g of x is equal to, and I'm going to leave off the x's here, is equal to f times g prime, or the derivative of g, plus g times f prime, or the derivative of f with respect to, in this case, it would be x, because I have my independent variable as x, right there. Okay, so we have y is equal to x times 3 to the 2x power. So y prime, I'm just going to apply the product rule but not actually work through the derivative process. I'm just going to write y prime is equal to the first factor, x, times the derivative with respect to x of 3 to the 2x power, plus the first, or the second factor, 3 to the 2x power, times the derivative with respect to x of x. And really, we know the derivative with respect to x is equal to 1, so we just need to really work on this exponential function with the base that's, well, 3, base a. Now, I'm going to step off and just reveal the solution, because I'm going to work this like I did in my previous example. It's very much, well, it's practically the same. I'm going to show the work again of converting this into base e, and then going through the process through the natural exponential function, or use that rule for the derivative of natural exponential functions, as opposed to using the new rule where we can, find the derivative with just simply base a. You can do the solution any way you like. If you're going to remember that new rule, great. If you think you might forget it or struggle, because we're not going to use it that much, you can go to, again, that base E and use a derivative rule that you already know, hopefully. Okay, so yes, working our exponential functions into a base E and not using the new rule that we have for doing it for any base A, is going to take a little bit more work. This looks like a lot more work because I'm showing every step in hopes that you can follow my work better. So this looks like even more, again, if you did it on your own, probably can do a little bit quicker. And we have, if a is equal to 3 to the 2x power, then a prime is equal to 2 times the natural log of 3 times 3 to the 2x power. So let's go ahead and replace that, or do that derivative with respect to x, which I just did. So we have x times, this here is going to be 2 times the natural log of 3 times 3 to the 2x power plus 3 to the 2x power, and the derivative of x with respect to x is just 1, so it's just 3 to the 2x power. Okay, now, again, don't lose points oversimplifying your answer. If your teacher is happy with this, or if this is going to be acceptable on some kind of standardized test that you take, then leave it. And it's perfect. We've applied the derivative rule, and you know, we finished our calculus, but if we want to do some more algebraic steps to simplify this, or if you're required to, both of these terms have a factor of 3 to the 2x power, so we can write y prime is equal to 3 to the 2x power. These parentheses are there. I always do that with substitution. It's almost confusing a little bit because it seems like you should be distributing this x, but of course there's only one factor, or excuse me, one term in here. So this term, I'm taking that 3 to the 2x power out, and that's going to leave me with 2 times the natural log of 3x, and then over here, plus 3 to the 2x power divided by 3 to the 2x power is just equal to 1. And that's a final answer, unless you want to, again, simplify this 3 to the 2x power and write that as y prime is equal to 3 squared to the x power, undoing that power to power rule, if you will, and 3 squared is equal to 9. So you might see this answer as 9x, 9 to the x power, times 2 natural log of 3x plus 1. All right, next example. This example, like the last, is going to require the use of the product rule. And as long as you remember to differentiate with respect to theta, because that's the independent variable in our function, and you remember the derivative of sine is cosine, and we do have a theta or a pi theta in here, so we'll have to use the chain rule when we do the derivative of that sine. This is, you know, basically the same type of question as the previous problem. Again, just a little bit more difficulty with the trig function, a little bit of chain rule, and we have an independent variable of theta as opposed to x. So I'm going to step off, reveal the solution one step at a time, not really talk much about it. If you want to pause the video, give it a shot, or just watch the answer being revealed. But of course, practicing on our own is always a good idea. For our last example, we're going to find the equation of the tangent line at pi over 2 pi for the function y is equal to 2x, and the x is raised to the sine of x. So it looks like this goes right along with the problems we've been doing in this section so far, where we have a variable in the exponent. except unlike the previous three examples, we also have a variable in the base. So let's recall a couple of rules for finding derivatives that we've had so far this year. Ta-da! Alright, why am I bringing this up? Well, we've got this rule for finding derivatives of exponential functions, of course what we're working with right now in this video. And and I showed you how we can use the rule just the way it is and memorize it, or go in and out of exponential form and natural logarithmic form, or just logarithmic form, and change the base from base A to base E, and use rules that we already knew, and practice our use of logarithms. Well, the definition or the rule that I gave you said that A was a real number not equal to 1, so it was a constant and the variable is in the exponent. Whereas in the general power rule, we have, and this is set up for u substitution here, but we have u to the n is equal to n times u to the n minus 1 derivative of u with respect to x. Well, this is, the variable is in the base and the exponent is a constant. So we don't have either one of those situations here in this problem. We have a variable in the exponent, we have a variable in the base. So how I've been doing all these problems without just directly using this this u substitution form and going in and out of logarithmic and exponential form and effectively changing the base, we can write this into a form that will allow us to finish the problem, because right now we don't have any direct rules that are going to apply. So let's put this, let's take the natural log of both sides of this equation. We have the natural log of y is equal to the natural log of 2x sine of x. Now we're going to make both sides of this an equation, an exponent of e. Effectively, I want to, get it back to y is equal to, get back into the exponential form. And we have y is equal to e to the natural log of 2x times the sine of x. Now we still have a variable in the base and a variable in the exponent, but and maybe I could expand this and rewrite this now to where you can see that this variable in the exponent is going to come down in line with the variable in the base and allow us to finish the problem. But I want to just go ahead and set up my u substitution now, because ultimately to clean up for my final answer, I am going to let this base e and this log base e, natural log, go ahead and cancel out in that form. So just to keep my work, in my opinion, a little bit neater. So we're going to say let u equal the natural log of 2x sine of x, and we're going to go ahead and expand this logarithm. It's the log of two things being multiplied together, which is equal to the log of each of those separately and then added. So this is going to be equal to the natural log of 2 plus the natural log of x sine of x. And now that we have this isolated, we can go ahead and let this exponent come down with the power property of logarithms and come in line with that x. Oops. All right, now to actually do the derivative or find the derivative of u with respect to x, well, this is going to be constant, so that's 0, and we're going to use the chain rule, or the product rule over here. So we're going to have the sine of x times the derivative of the natural log of x, which is going to be 1 over x, plus the natural log of x times the derivative with respect to x of sine, which is going to be cosine. So du dx, or u prime, is equal to the sine of x over x plus the natural log of x cosine of x. So coming back over here, what we have then, see, this is my u, so I'm really just doing the derivative. Let's come over here. When I find out what u prime is, I'm just really doing the derivative of e to the u, which is e to the u times, of course, u prime, which is this right here. So y prime is equal to e to the natural log of 2x to the sine of x power times all of this, which is going to be, of course, just copying this over. Voila, sine of x over x plus natural log of x cosine of x, and now this e and this natural log can go ahead and let those inverse math operations cancel out, and we just have y prime is equal to 2x times the sine of x times sine x over x plus the natural log of x cosine of x. But now that I know what the derivative is, I can use that to find the slope at pi over 2 and ultimately find the equation of the tangent line at that point. But I'm running out of space, and just to clean up the video a little bit, let's pause. And not only pausing, but let's go ahead and find that derivative at pi over 2. I'm going to clean this up in a second. It falls apart pretty easily, and the answer's not too bad to figure out, but just went and wrote all that out. One thing I also want to talk about is when you look at this derivative of our original function, the natural log of x is actually part of or within the derivative function. And you can't take the natural log, or the log of any base for that matter, of 0 or a negative number. So this derivative is only defined for x's that are greater than 0. And indeed, if you go back up to here and you put this into your calculator and graph it, you'll notice at the negative side of the x-axis, when x is negative, that there's some very interesting things going on here. It gets a little crazy when x is negative. So this derivative is only defined for where x is greater than 0. So thankfully our point is we're being asked to find the equation of a tangent line at pi over 2, which is positive. Well, we have, let's see here, the sine of pi over 2 from the unit circle is 1. So we have 2 times pi over 2, which is going to cancel out and just be pi. Over here, we have the sine of pi over 2, which is again 1, over pi over 2, plus, I don't really need to worry about trying to figure out what the natural log of pi over 2 is, because the cosine of pi over 2 is equal to 0. So this whole term becomes 0, and we get pi times, let's see here, well, 1 over pi over 2 becomes pi times 2 over pi. Those pi's cancel out, and the slope of our tangent line is equal to 2. So the equation of our tangent line at that point is, and I'm just going to leave this in point slope form, is y minus pi is equal to 2 times x minus pi over 2. And that is the end of my last example. So, I'm Mr. True. Go do your homework.